remember that the assumption here is not only that there are arrivals, but also there are departures. Okay? In the closed network, there are neither arrivals nor departures. Okay? So if I had no arrivals, but I did have departures, then lambda equals 0 would be correct, and that would be an extremely boring queuing system to look at because nothing is happening in steady state. Okay, so there are two issues. Lambda, all the alphas are equal to 0, and there's 0 departures. None of these are greater than 0. They're all equal to 0 for all the nodes. Okay. So nothing is entering, nothing is leaving. The number of items in the network is constant, so we have this number. So that capital N is another parameter of the system, the number of items that are in the system. Okay, that's staying constant. So the parameters are the PIJs and the mu's and N because we don't have any alphas. So in that case, so I go back to this. If I put in alpha equals 0, I get lambda equals P transpose lambda. So this operation, well, it turns out I won't be able to do this operation because of what I said about the P's. I won't be able to invert this matrix. Okay? Because of that restriction that the sum of all the P's is equal to 1 for each node. So forget about all this. So I still have lambda equals P lambda. But then, in order to do this, did you do something? Stop that. Eatery? Is that the food court? Is that ready?
Yes.
All right. I'll talk about this, and then we'll put on the food court. So first of all, the number of items is going to be constant, and this doesn't have a unique solution. And then somebody figured out a trick, basically. If we have, so it doesn't have a unique solution. In fact, if there's one solution, then there's an infinite number because I can just multiply them all by a constant. Okay, because if lambda star is a solution, then S times lambda star also satisfies that. So if I know lambda, I also know mu, so I can calculate. Well, this is messy, and as I say, this is all a trick. Choosing a lambda that satisfies this, one of the infinite number that satisfies this, I can calculate all the rows, which are all sort of artificial also. And then I can define this quantity, which is sort of provisionally, that 0 means it's not really the probability distribution, but it's sort of provisionally the probability distribution. So here's this artificial row based on this artificial lambda. Okay, but it's a function of this arbitrary variable. I'm sorry, I'm using S again. It's not the number of servers anywhere. It's just an arbitrary quantity. So basically, we can normalize this provisional probability distribution by the sum. And the reason is, what I'm doing here is I'm adding up all of these pi's where the number of items in the system is exactly equal to n. Now there are a lot of different ways that could happen, so this could be a big summation. When I do that, the first thing that happens is that all the s's cancel out, because this is going to be a product of a lot of s's, and I'll have the same number of s's in the denominator, and so all the s's cancel out. So that's why I say this is a trick. Don't get too hung up on this. So that gives me a probability distribution, and then once I have that, I can calculate anything I like. And it turns out that this denominator there are nice ways, and by nice I mean there's closed formulas, there's algorithms and so forth. Other than that, they're not nice. But you can calculate this, and therefore you can get the probability distribution. This will not be on any test or homework. Don't worry about it. But this is what's going on. Okay, I'm going to do an example, but before we do that, we have the food court, or are you still programming? All right, so let's look at the food court. This is, in case anybody's not hungry, this will get you hungry. HDMI, do you have that, or do you? Okay. Yeah. All right. I am seeing this for the first time also. So therefore, I will stand back. Oops, wait a minute.
I think it works even if we keep it here.
All right.
That's just meant to, yeah.
Okay.
Affix to your
Do you hear us? Yes.
Yeah, so I have not incorporated the palette thing and the place where people sit that I have to still have to do with it. So right now, like...
You need the pointer?
No, I was just taking to the slides.
Oops.
Yeah, pretty much this, except for the tables and people coming out with palettes or the plates in their hands. So here, like the way I have selected it right now is like made it that people of different colors so that you can see them. Green and orange people will enter and they will go to any of the queues depending on, like, we can set the different parameters as to how we decide which queue they will go to, like maybe a certain fraction of people going to get either of the three stuff, or people going to any queue which is the smallest queue. We can play with all those parameters, and then you can see how the queue builds up in front of each of the three different places, Pizza, McD and Froyo, and then they go to a billing queue where there is just one queue for the billing counter, and finally they get out of the eatery. Just a representation to get a better idea.
The American version of a food court, you pay at each of the vendors.
Yeah.
I guess this is an Indian version of a food court.
Yeah, quite maybe. We can do that as well. So we can just play with the parameters to see how queues build at different places and simulate a real food court. Like, that's the essence of showing it, I guess.
So you have two classes of customers there, the green people and the orange people.
So the green people and the orange people, coming from the two different gates. I'm just showing how they are, like, colored them differently to identify them. And finally, people there are like yellow people coming out of Pizza, pink people coming out of the McD, and green people coming out of the Froyo in the final queue. So
so it looks like the billing station is kind of a bottleneck, right?
We can kind of change its parameter, like how fast is it, like people are operating there to Okay,
why don't you speed that up?
Yes.
So, as I said, in real life, people don't stand on each other's
So right
shoulders.
now it's like we have run it for 500 seconds and we see a maximum content of around 50 in the final one.
So if you're designing a food court, the first thing that you learn from that is that you better get a faster checkout clerk.
Yeah, so I'm like reducing the processing time from, let's say, 6 to 3. I'm assuming that they are processing it at the same rate. Does anyone remember what the numbers I said? 50 was the queue size, and how many seconds? Sorry.
Oh, the max queue size.
Well, clearly, it's different now.
Clearly, it's a lot different. Yeah. So it's never going beyond 8.
So we've hired.
So now we see that the other queues are.
Person who's too fast.
Those 3 queues are building up, kind of. Those 3 queues are building up right now, like in front of the.
Did you change the arrival?
No, I didn't change anything. I just changed the processing time, the billing time, basically.
But you've also you've sped up the clock.
Yeah.
Yes, yes. Your
Okay,
simulation is going
so
fast.
before we would have had also a build-up, you just didn't run it that fast.
No, the build-up previous time. Oh yeah, yeah. Because
Okay.
I haven't changed anything, we'll see those build-ups as well. But here there is no build-up right now, like at the billing counter.
Not at the billing counter, but you're gonna have to wait a long time to get your food.
Yes. That's where simulation comes into picture, and it will help us design our system in a better way.
Is there a way to, in this software, put something where somebody decides to go to Q1, but if there's like a backup, or if you've reached the maximum, that the person decides to go to Q2?
Yes,
from
yes,
Q1?
you can decide, you can play with all those parameters. Do you want to go to a specific queue? Do you want to go with like by certain percentage? Or do you want to go to the smallest, like where the queue is the smallest? You can play with all those parameters. It has got all those
Oh,
features.
I forgot to ask you about the other queues, the multiple server queue. Did you do that one as well?
MM3?
Yeah.
Yeah.
Oh, you did that? You should have reminded me. Why don't we look at that, actually? We should have done that first.
Yeah, I think this is it for this eatery.
Remember, there's the tutorial today on how to do all the amazing things that he's doing.
It's pretty straightforward if you spend a little time.
Video that too, so those that comment it.
Yeah, I think we can do that. Yeah.
You know, in scheduling this thing, we found out that there are certain rules about extra classes, and we had to assure the scheduling people that this was optional. This is not a requirement. And one of the arguments that we used was that he was able to learn it in a couple of hours without a tutorial. So therefore, you could probably learn it in not too many more hours without a tutorial.
But yeah, we'll record it. Yeah, don't worry. I tried to find a time which was suited to like most of the people, and this is the one I found. I guess there are 4 people who are not able to attend. Sorry, we don't have people here. So this is the MM3 Queue, which we went through it some slides back. I don't remember the parameters, but all the 3 machines, like all the 3 processors are at the same rate.
So it looks like you might be exceeding the capacity by a little bit, because it's, of course, it depends on the speed. But the queue is growing.
Yeah. So the inter-arrival time is 5, and the processing times. Oops, sorry. I got a box rather than the processing. And this is 20.
6.6.
Yeah.
So it's 2.
3 by 20.
So well, see, the problem is that it doesn't work in terms of rates.
Yeah.
The data doesn't come in terms of rates.
Yeah, I'll just like do it to 10, but in this case the queue won't build up, I guess, at all. If I do it for all the 3 at least.
So one of the things that's annoying about the software is that, you know, it's, for me, it's natural. I mean, for them, it seemed to be natural to work in terms of average times. But for us, it's going to be natural to work in terms of rates, which are just the inverses of that. So here, if the arrival rate is greater than the sum of the processing rates, 3 times the processing rate, then we're going to have a problem. So if the mean time between arrivals is less than the sum of the the inverses.
Inverses, yeah.
Yeah, so that's annoying. So you had an arrival rate of, you had a mean arrival time of 5.
Yes.
And the service times were 20.
Yeah.
So that means that the service rates were 1 over 20,
Yes.
right?
Into 3.
And you had 3 of them.
Yeah.
So the total capacity was 3 over 20.
Yes.
And the arrival rate was 1 over 5,
1
which
over
is
5.
4 over 20.
Yes.
So that's why it exceeded the capacity.
Yes.
Okay.
And right now, yeah, I changed the processing times to 10, in which case it becomes completely opposite, and you never you don't see the queue getting built up.
Is it again random to which parser you go, or is it based on which one is busy at?
Whichever is free, I
Remember
can
what happens-
change it. We can play with it.
Yeah, I mean, as the assumption in the model, which I think you followed, is that
Whichever becomes free first.
yeah, whichever one is free. You know, of course, if more than one is free, I guess then you're flipping a coin and it doesn't matter. But if only when one becomes free, then that one takes the next guy in the queue. But we were talking about other versions of this. You didn't get around to that, right? Or did you?
No, not really. I had to.
For example, another version would be to have 3 queues, okay? And that's just 3 queuing systems in parallel. And it turns out that this will give you better performance, less waiting time than if there were 3 in parallel. And we were looking at other kinds of disciplines and so on, but, you know.
Yeah. Maybe some of them we can have as a homework assignments.
Good. Good.
Can you set up individual queues in front of the server and another queue right behind it?
Yeah, you can. You can.
You mean like one joint queue leading to 3?
Yeah.
Yeah, sure, you could. Okay, so that's all for today. Unless there are questions, are there more questions? Okay, in that case, see you Thursday. Oh, wait, the tutorial today or Thursday? Today, okay, today. Oh, today's Thursday already. Oh.
Time flies.
Time flies.
Excuse me. Everyone is requested to place their assignments there.
Can I ask you a question about slide 88?
Let's do it outside, because somebody's going to be coming in here.
Yeah.